Okay, so now we will continue with the Gauss-Jordan method. In fact, it is we know that it's a variant of a Gauss elimination. In this case, what we did was we both eliminate the variable from the equations which are numbered both before and after the pivot equation. So for this purpose, first I will change the name of it. So let's write here Gauss. Jordan. Then I will save it with Gauss Jordan, name Gauss Jordan. Okay, now I have changed it. Now the point is I will delete the parts for large matrix here. I don't need it. So the CPU time and other things can be deleted as well. I don't need these lines. But it may be good to keep the condition number. So we don't need the parts for scaling. We can use scaling, but it's meaningless. You can do the also pivoting only once. I will just delete it. So I have the pivot equation. I don't need the parts for the back substitution. Now let me change the CPU time for elimination, because we just eliminated. And we don't need this. Part. So let me delete these empty parts. Now here, as you see, I have an iteration from I plus 1 to n. Now I will copy this and I will add in another loop here. Now this iteration I2 in this case will be from 1 to I1 minus 1. And this will be the only difference that you need. This is the only difference between the Gauss elimination script and the Gauss-Jordan script. So certainly I will make an iteration beginning from the first row to the I minus 1 row. Okay, so when I1 is equal to 1, this becomes 0, and 1 to 0 will not make any iteration because it will tend to increase one by one. So let's see whether it will make an iteration. I will just put a breakpoint here. Okay. And I said that run next line, F10. Now here you see I1 is 1, therefore this is 0. So it will tend to run from 1 to 0, and it passes directly to the next one. So it runs through 2. And let's look at the matrix now. You see the first row is eliminated. Now I will go it gives an error. In 22. Okay, so I didn't change the n, so it tends to run n from 1 to 100. Sorry, it was my mistake. Okay. And let's check it again. Okay, first column is eliminated now. Now I go to the pivot. So I take the pivot. Now I1 is 2. So let's run. Now it will run from 1 to 1. Let's check for the A now. You see the first row is eliminated. For 3, it didn't run from 1 to 3. Why it ends? Let's see. Yeah, this has to change now, not n minus 1. It has to change from 1 to n. Yes. So it's 1 to n, n plus 1 to n, and it will run like that. Okay. Now let's run it once more. Now it should be okay. Let me check it now. Okay, first column is eliminated now. Let me check it. Second column is eliminated now. Yes, now I have a diagonal matrix. Now certainly I can do another operation here at the end of each line. I can divide the B's to the A's. Now here, instead of doing it like this, what I'm going to do is like that. I have the diagonal terms. In fact, I can do it like this. I just want to show you something else. In fact, there are many ways of doing this operation. So x I1 is equal to a I1 I1. Here you can normalize the whole line with the AI1 after making the row column elimination step. But I just want to do something else. Now I have the x's here. I will put a breakpoint here. I will eliminate the first breakpoint and I say the continue. Okay, now the elimination is done. As you see, I have the diagonal terms in the x, row vector of x. Now the point is this. So I have B here. And B is a column vector. So what I'm going to do is x is equal to transpose of x okay. Now I need to divide B with x, and I will say x. I exit from the debugging mode. It will probably give me an error. Let's see what it gives to me. Yes, unrecognized. Oh, T has to be small. It's another thing that I expect. So B's are these values. There is a problem. Let's check what the problem is. I will set another breakpoint here. Now the x are okay. And I just want to get the transpose of it. That's also okay. And I want to divide B with this value. Okay. Now I will put here a dot. Now what it means. So remember that B is a column vector and X is a column vector too. So basically each element of the B will be divided by the each element of X if I put a dot here. Let's see whether it will work or not. Again, I will put a breakpoint here and say run. Okay. Now I have the B value, I have the X value. Step forward. Now I have the result. You see, this is how you can make operations element by element on arrays in general. You can do it if B and X has the same dimension. For example, you can multiply them. And what it will do is it will multiply each member. You see, each member is multiplied. So it is 3 to 1 column vector. This is a column vector, and the result is a column vector as well. Of course, for Gauss-Jordan, it has to be division. So this is the script for the Gauss-Jordan method. I didn't have start time. Let me copy this one. Perhaps I deleted it. So let's put a variable here. Yes, now I have the results. Okay, so this is the script for Gauss-Jordan.